Good morning, children. Hope you're keeping healthy, pretty safe, right? So, we are going to begin with Unit 9, that's coordination compounds. And this chapter is, we're in coordination with D and F block elements. So, in the previous chapter, we already learned that transition elements are all such elements which have unpaired electrons in their d orbital. And you also learned that transition elements participate in complex formation. And that is what we are going to learn in this chapter, what exactly is meant by complex compounds. So let us get started with this unit of coordination compounds. Let me give you a brief idea. Let us say M is any metal which is a transition metal. It could be any metal of 3D series. For example, it could be chromium, it could be copper, manganese. Over here you can see I have highlighted here is cobalt. Fine. This metal atom has unpaired electron in its d orbital, right? It might be 1 electron, 2 electrons, 3. Whatever might be the configuration, depending upon that, we have number of unpaired electrons in the d orbital. So to compensate the this d orbital, what happens? It participates in the bonding with ligands. There is a term called as ligands. So there is a need to understand what exactly is meant by the term ligands. So all ligands are such compounds, remember, which have lone pair of electrons. That's a must to have. So I repeat, all ligands should have lone pair of electrons. So only if they have lone pair of electrons, they are in position to donate those lone pair of electrons to the central metal atom through a bond called as coordinate bond, which means there is a donor and there is an acceptor, right? So when they form a complex, let me give you a brief diagrammatic representation. Let us say these are the ligands around the metal atom, okay? Let us say there are 4 ligands. Okay, we can mark it with blue. Fine. So these 4 ligands around the central metal atom M have an ability to donate the electrons into its empty d orbital. And why do they have such an ability? Because of the presence of lone pair of electrons. And since there is a coordinate bond between the metal atom and the ligand, therefore such complexes are known as coordination compounds or coordination complexes. So that's a general idea about it. And if you remember, in grade 11, you have learned about the term Lewis acids and Lewis bases, right? So try to recall, Lewis bases are always electron rich. I said Lewis bases are electron rich, whereas Lewis acids are electron deficient. That means they are electron acceptors. So they are deficient of electrons, right? So over here, if I ask you whether metal atom is going to act as a Lewis acid or a Lewis base, what's your answer? Of course, yes. Because metal atom belongs to D block, that's a transition metal, and they have unpaired electrons in their d orbital. That means they are deficient of electrons. So all central metal atoms in case of complexes are Lewis acids. Remember this point. Wherein just now I spoke about that ligands are rich in lone pair. That means they have an ability to donate those electrons. So since they're electron rich species, it's very very important to understand that Lewis bases are your ligands. So in a complex, you have an association of Lewis acid with a Lewis base with the help of a coordinate bond. And why do we call it as a coordinate bond? Because it is one side donation. So ligands are your donors and metal atom is your acceptor. So remember these terminologies, it is very very important to understand. Now here I have given you one very clear example to give you an idea what exactly is the structure of a complex compound. So as I said, a complex compound is in need of having a central metal atom, which usually belongs to a transition series, right? So here you can see cobalt, which is a transition metal. It belongs to 3D series. Fine. Now since it is electron deficient, right, it is in need of electrons. So who are going to be the donor for such metal atoms? Those are none other than ligands. So where are the ligands in this structure? Let me highlight it for you. Ligands are Cl2 and NH3, right? So Cl2 ligand is known as chlorido. That we'll be learning little later. Just keep in mind the term chlorido. And NH3 is known as amine. I repeat again here, where are the ligands? Can you just say, yeah, Cl is one ligand and NH3 is the another type of ligand. So Cl ligand is an ionic compound, okay, is an ionic in nature. So this entire complex becomes ionic in nature as well. So that's the reason you can see a plus charge on this entire complex. Now remember one very important thing. When I say complex, can you see the square brackets over here? So everything within the square bracket is your coordination complex. So all coordination complex carry a charge because they are made up of metal atom. Indeed, I must use the term metal ion. That you will be understanding little later. So just keep in mind that here we have to use the term metal ion. Apart from that, ligands. Ligands are also having a certain amount of charge. For example, Cl. Cl has a -1 charge. We all know that. And NH3, which I am calling it as amines, is not having any charge. So this set of series of ligands I'll be giving you in my lectures, and what are the charges we have to memorize, that also I'll be sharing with you. Fine. Now if I ask you how many types of ligands are there, so we can understand very clearly over here that there are two types of ligand. One is Cl minus and the other type is amine NH3. Next important thing is, if I ask you how many ligands are there, so we have to be specific about their number. So you can see here chlorine is 2 and NH3 amine is 4. So what is the total number of ligand over here? 6. So the total number of ligands over here, I'll write it down here, comes to be 6. And the number of the ligands which are coordinating with the central metal atom also helps you to understand about coordination number. Therefore, 4 plus 2 is 6. Hence, the coordination number of this complex is 6. Okay. So this is a brief idea. Hopefully you understood. I just repeat once again. A coordination compound is made up of a central metal atom which usually belongs to transition series. Along with that metal atom, there are ligands which are bonded with coordinate bond, and ligands can have a charge. They can be positive, negative, as well as neutral without any charge. For example, here we saw amine, and I said amine doesn't have any charge. Whereas when I talk about Cl carries -1 charge. Apart from that, we also have to take care of the number of the ligands. So here in this, the number of ligands are 6. Therefore, the coordination number becomes 6. Remember. Another important thing to understand over here is within the square bracket, what is written within the square bracket, I repeat, is known as coordination complex. And coordination complex carries a charge. It can be positive charge or as well as negative charge. But right now in this example, what has been highlighted is a positive charge. One very important thing, another atom you can see, not atom I must say, it's an basically another ion, right? Like for example Cl minus. So this is written outside the square bracket. So whether it is an atom, ion, whatever it might be, usually it is an ion. It can be cation as well as anion. Which is written outside the square bracket is known as ionizable ion. So here, since it has a negative charge, so we are calling it as ionizable anion. Remember, this point is very, very important to understand. Okay, another important thing, if you note down, the charge on the complex is +1 and the charge outside the complex, the species what you have here, Cl minus, carries -1 charge. So observe it very carefully. That means the charge on the complex should be equal to the charge on the ion which is written outside the square bracket. That means the ionizable ion, right? So whatever charge this ionizable ion carries, that should be opposite to the charge on the complex. That's very important thing to be understood over here. So in general, I have described everything. And yes, another term you can see over here I have written is coordination sphere. So this square bracket and everything within the square bracket I said is known as coordination complex, and therefore the square bracket term including metal and ligands together is known as coordination sphere. Fine. So we have understood all these terms. What is a coordination complex? Let us go ahead. So all these things I have described here one by one. That's first thing is coordination compound, what I spoke just now. Okay, another very important thing is these coordination compounds never dissociate in water. So I've written here, they do not dissociate into simple ions when dissolved in water. That means you can't separate out metal and the ligands from each other. But yes, this ionizable ion is given out in the solution. But the metal atom and the ligands can never be separated. Remember, mark my words, metal atom and ligands can never be separated. They can't dissociate, okay? But yes, the ion which is ionizable, that's why it is called as ionizable ion. It gets into the aqueous solution as a separate ion. So this complex remains one and ionizable ion dissociates. Fine. So here you need to understand that complex we are talking about which doesn't dissociate at all. That means metal atom plus ligand will always remain together. Fine. Now there is another term called as double salt. So that's the difference between coordination compounds and double salt. That double salt is made up of two salts. I say double salt is made up of two salts together. For example, Here we can see in this example very well. Yeah, let me just highlight this for you. This is here, okay, down. NH4 whole twice as a subscript. So this double salt, when we are talking about, that's Mohr salt, it is made up of, let me highlight it for you, FeSO4, that is ferrous sulfate, which is one compound, and ammonium sulfate, which is another type of compound. So when two salts combine together, it is known as double salt, and they are in the form of crystals. This you will be preparing in the lab as well. Mohr salt preparation is there in your syllabus. Now, what happens when such salts are dissolved in water? They do dissociate into simple ions. So, here dissociation occurs and they will dissociate into ferrous ions, sulfate ions, ammonium ions, NH4 plus, right? So, all such ions get dissociated, okay, from each other. That means when you dissolve Mohr salt in water, it is going to fetch you all these ions in aqueous solution. So that's very very important to understand, and that's the basic difference between double salt and a complex compound. Fine. So these terms I have already described like before. Coordination entity. Coordination entity means what is sitting within the square bracket. Here, if you can see, this entire thing from cobalt, that means within the square bracket, which consists of cobalt, a central metal atom, Cl2, a ligand, NH3 whole 4, another type of ligand. So this entire thing which is within the square bracket is known as coordination entity. Okay, so this we have understood very clearly over here. Fine, let us move ahead. Now, what do you mean by counter ions? Counter ion is basically your ionizable ion, which I described there in the first example as Cl minus. So any ion which is written outside the coordination sphere is known as counter ion. It is called as what? Counter ion, and it is present outside the coordination sphere. For example, in this complex, if I see, okay, let us take this example. K4, within the square bracket you have FeCN6. Let me close this bracket here. Yeah, it's like this. So within the square bracket we have what? What do we have here? Yeah, just make me this one. Yeah. Now K4 FeCN6, when I say within the coordination sphere you have iron, right? Fe means iron, and Cn is basically your cyanido. Okay, that name we will be learning. Cyanido is acting as a ligand. Iron is acting as a metal atom. So there is an association between metal and ligand within the square bracket, right? So what is written outside the square bracket? And yeah, you might be thinking that in the example which I discussed before, this ionizable valency was towards the right side. And here what happened, that the ionizable valency went here. Yeah, what's the difference between the two? Tell me. Just let me set it for you. Yeah. Yeah, tell me. So what do we understand with this term? So counter ions are present outside the coordination sphere, but it doesn't make a difference whether it is present towards the left side or the right side. Yes, it makes a lot of difference. Though whether it is written towards the left or right, it still remains what? Ionizable ion. But can you wonder and can you notice what is the difference between this and the one which I have written before? See here, potassium. Potassium has a plus charge, wherein in the first example the ionizable ion which I discussed was Cl minus. So it is a convention whenever we write the formula of any coordination compound, we are supposed to write cation first followed by anion. I repeat, it's a convention when we write the formula of a coordination compound, we first write cation followed by anion. So in the previous example, the entire complex was a cation and Cl minus was an ionizable anion. So it was towards the right side, right? But here the entire complex, this entire complex is an anion. It carries a negative charge, and the potassium, which is basically your ionizable cation. Therefore, first of all, we have to write what did I say? Cation followed by anion. Therefore, potassium is written first followed by this entire complex. Very, very important point to make a note. Okay, so we understood what are counter ions, and we also understood these terms like coordination entity, and of course now that's another important thing we need to understand about central atom. Okay, so what is the central atom? We already understood before. Central atom usually belongs to transition family, that is D block. So in the coordination entity, the atom, which it can be an atom, and I told you it can be either ion. How ion? That we'll be discussing with an example, to which a fixed number of ligands are bonded. And these ligands will give you a particular type of spatial arrangement that we will be talking in the concept of isomerism. So as of now, just keep in mind that ligands which are surrounding the metal atom, they will align in such a way that they will have a particular spatial arrangement in 3D space, right? So now what important I want to tell you over here is the central metal atom has a charge on it. How to calculate that charge? That charge is basically known as oxidation number. As you calculate the oxidation number before in the redox chapter you have learned in grade 11, and in the previous chapter also I gave you various examples where we calculated the oxidation number. So the logic remains the same. Let us work out one example for that. A very simple example here. Again, I have taken the example of potassium, and inside the coordination sphere it's iron with cyanide. Now see here, potassium has a plus charge. We all know that. But how many atoms of potassium are here? 4, right? So, and I told you in the beginning, the total charge on this cation should be equal to the charge on the complex. So if one potassium atom has a plus charge, so 4 atoms will have what charge? Plus 4, of course. So since these K4 will carry plus 4 charge, so what should be the charge on the complex? Minus 4. Did you get me? Fine. Now if you want to calculate the oxidation number of iron, because oxidation number, remember, is always of the transition metal which has been taken as a central metal atom. So we'll take it as X plus the charge on cyanide is minus 1. That you have to memorize. I'll give you the list. Into 6, because there are 6 atoms, equal to the total charge on the complex. That's minus 4. So X minus 6 equal to minus 4. So X comes as plus 2. And the oxidation state is always written in Roman numbers while writing its nomenclature. That we'll be learning. Okay. So if I say what is the state of iron here? Iron is in plus 2 state. Fine. So I think I made it very clear to you. Ligands, I have already spoken. They are all Lewis bases. They contain lone pair of electrons and they have an ability to donate those electrons to the central metal atom. And I also mentioned that ligands can be neutral, positive or negative. So all such examples we'll be discussing shortly. Coordination number also I discussed with you. The total number of ligands, I underline here, the total number of ligands which are the donor atom directly bonded to the metal atom gives you the coordination number. So in the previous example we saw the coordination number was 6. Now here in this example also there are 6 ligands. So the coordination number is 6. Coordination sphere we have already discussed that whatever is within the square bracket is called as coordination sphere. So collectively metal plus ligands. Counter ions I have already spoken. Now it's coordination polyhedron. That was what I mentioned about the geometry, the spatial arrangement. This I'm not going to explain right now because you won't understand. When we'll talk about isomerism, then we are going to take this point. But remember, polyhedron means the spatial arrangement of ligands around the metal atom. And in this portion of yours, you have only 3 spatial arrangements. That's square planar, tetrahedral and octahedral. Let me just tell you one important thing. Square planar means coordination number is 4. Tetrahedral also coordination number is 4. And octahedral doesn't mean 8, which you learn in maths, your polygon. It doesn't mean that. Here the coordination number is 6 in chemistry, right? So octa in chemistry means 6. Fine. So this we will be discussing about denticity in next lecture. I hope this is clear to you, and revise everything because these terms are very very important, and we'll be discussing soon about rest of the things. So thank you all and be happy.